Okay, you're all the way to lecture 9 now, and we're very much into the bulk of go into more into the engineering aspects. Now, this set, now if you, let me put it this way. If you like the previous material from the previous lecture, you're going to love this one. In the sense that what we're going to study is going to be a continuation of all those formulas and estimates of different types of intermolecular forces, leading to van der Waals and dispersion interactions and so on. But if you have the patience to kind of carefully follow the lecture, by the end of the lecture you're going to see also already some results of what we have been studying. So you're going to see some applications of these formulas which immediately lead to practically important results. I wish I had a picture of that, but I don't, so this is actually a copy from the book. Again, like something that you can think in mind, have this in mind for some point during the lecture when you're going to answer this question. Now, you have probably heard of the particular behavior of liquid helium. If you take liquid helium and put it in a vessel, what happens is it climbs up, then goes down the walls and spreads all around. So liquid helium is particularly hard to confine in a vessel. It goes up the walls and then it flows out. Now, what is the reason for this behavior of the liquid helium? Why don't other liquids do that and liquid helium does this? Apart from being of low density, of course, there is something specific that makes it climb walls of vessels. This is, you should know that this is a very good point because we're going to come to the issue of refractive index towards the end of the lecture. Now, it is not the low refractive index itself which makes the helium climb up the walls. But it is very important to know that the low refractive index actually is going to bring us, by the end of this lecture, is going to bring us to the molecular properties of the liquid helium, which are important in this case. So the low refractive index actually is an indication of something that's related to the van der Waals forces, which we're going to study this lecture. And then I wish to remind you that we still haven't answered the question from the beginning of the previous lecture, which is why metallic nanoparticles so readily aggregate and why is it so hard to disperse them again when they're in water. So hopefully we should have the answers to the question why liquid helium climbs walls and why metallic nanoparticles stick together so strongly by the end of this lecture. And as a first slide, let us summarize where we are compared to all different types of interactions that we have studied and that we're going to study here. So I have done all this summary of all the types of molecular interactions. Now, if you remember, in the last lecture, we started with charge-charged, and we have been going through charge-dipole, dipole-dipole, the case where we have an interaction between a charge and rotating dipole, which is the case in reality because any molecule can freely rotate around. And we ended up with two rotating dipoles. Just as a reminder of what was what, let me write down the behavior of all of those forces as a function of the distance between the particles. So this one is dependent on just the inverse distance. No, that's charge. Energy. Charge dipole is dependent on the squared. Dipole-dipole, without rotation, is dependent on the inverse third power of the distance. Then we went here to charge rotating dipole, and it was dependent on what? Square. No, force. And finally, we finished with two rotating dipole, or the so-called Kies-Ohm energy, which was dependent on, if you follow, it would be 1, 2, 3, 4, 5, 5, but it's dependent on the 6th power, actually. And then what we have to do here is study what happens when we have a charged and polarizable molecule. Two polarizable molecules, one of which is a dipole, and then molecules which are polarizable without even being dipoles. If you continue along this line, you would expect that this is dependent on the inverse 10th power of the distance, but that's not the case. As you're going to see, everything from here on is going to be dependent on the inverse 6th power of the distance. And again, just in thinking physically in terms of basic physics, why do you have this the inverse power kind of being more and more increasing in this power? Now, charge is a very strong interaction, so it's going to operate on a very long distance. Once you replace the other charge with a dipole, this is already getting to be a shorter range interaction. So the distance on which this interaction operates will be smaller. Two dipoles, if they're very far apart, you don't have charge. I mean, from their viewpoint, they have electroneutral molecules. The way two dipoles interact with each other is just because they orient in some orientation when they're close. Let's say the plus here is closer to the minus, so it attracts strongly than the plus repels from the plus. So then again we have one power down in the distance. Now if you let the dipole rotate, the thermal energy tries to disorient the dipole with respect to the charge. So this is less favorable towards the interaction, so the power goes up even further. The inverse power goes up even further. And if you have two rotating dipoles, they are kind of tumbling all around, and just at some specific point they are going to attract each other. So then again you have even stronger distance dependence, so this means that this force is going to operate only on very short distances. So we know that already, and then the question is what happens when we have charged polarizable dipole. I started with this the previous time, so I'm using these two slides just to remind you. Now, you don't have a permanent dipole in the molecules, atoms, and so on. But you have induced dipole, because let's say if you have a hydrogen atom with electrons circling around the nucleus, then when you apply the field, let's say this is the positive side of the field, and this is the negative side of the field, the electron is going to get attracted to the positive side. The positively charged nucleus is going to be attracted to the negative side of the field. So you're going to have polarization. If you remember, any dipole is measured by the dipole moment, which is equal to the length of the dipole times the charge. In this case, this polarizability is equal to the molecular polarizability times the strength of the field. And the electronic polarizability is related to this, there is this expression 4 times pi, the polarizability of the material and the volume of the atom, molecule, whatever we have getting polarized. So if you have a molecule, this molecule is going to get polarized in very much the same way. Then, just to be consistent and kind of overview everything, we now know what electronic polarization is. This is the internal polarization of the molecule. We derive the formula what happens when you have a dipole close to an ion. This dipole is going to itself orient a little bit, so the negative side of the dipole is going to, on the average, is going to face the positive charge more than the positive side. So it kind of, in a way, maximizes the interaction. And this is equivalent of polarizability. So if you just take the average, now this is an expression in which I'm not going to go into detail, but you have this exponent here which tells you how much the orientation is dependent on the cosine theta. We derived this expression actually the last time. You are going to find out that you have the equivalent of orientational polarizability, which is equal to the dipole moment divided by 3 times kT. And because this is again has the same dimension of polarizability, you can say that the polarizability of any molecule, atom, or particle is going to be equal to the electronic polarizability plus the orientational polarizability. And this is where we start understanding the different types of polarization interactions. Essentially, we're going to plug this expression into the different expressions that we have obtained so far and see what happens with the interaction. Now, any questions so far? Okay. I hope you have some questions later when you start applying these formulas. Now, let's discuss this case now. What happens when we have an ion and a polarizable molecule? And I'm not going to go through all the derivation of the expressions here. What I'm going to do, I have compared what we have studied so far and the new expressions that are going to appear. And the idea is to focus on what's important, what's the physical important parameters and variables in these expressions. So let me remind you of the expression that we have obtained in the previous lecture, which tells us that the energy of the interaction between an ion and a dipole corresponds to the charge of the ion squared, the dipole moment squared, all those set of parameters, kT, and the radius on the fourth power. The distance between them to the fourth power. Now, why do we have kT here? Because the thermal motion is the one that tumbles the dipole. So this is from the previous time, the expression between a charge and a dipole. Now we know, however, that the total polarizability is equal to the dipole moment over 3 kT and the electronic polarizability. Electronic polarizability, the one that comes because the electrons are separated from the nucleus. Now, then I'm giving you here the formula right away. You can immediately obtain the formula. You substitute U squared here with the full polarizability here. And then when you replace the full polarizability with the two components from the Debye expression, you are having this very important formula for the full energy of interaction between an ion and a dipolar and ionizable and polarizable dipole. So essentially what you have here is a molecule which is polarizable, and it also may have a permanent dipolar moment. So this expression gives you the interaction between an ion and any type of molecule, a molecule which may have dipolar moment and which is likely to be polarizable. Actually, all molecules are polarizable. And now, this is again like fast thinking, waking up to some extent. Now, what is the relation between this formula and that formula? When you find this out, you're immediately going to see how this formula has a reason on the bottom. How do you obtain one from the other? It may not be this way, it may be the other way. Come on. I mean, it's just algebra. What do you do?
If in the bottom one alpha naught becomes 0, we get the top one.
Exactly. Now, if this one, the electronic polarizability is 0, we obtain this formula. So you can see how this formula eventually, so it tells you if you have a molecule which is dipolar but not polarizable, we're not likely to have such a molecule in reality. But if we have such a molecule, then this molecule is going to interact with the ion in exactly the interaction that we have studied already. If this molecule does not have a dipole moment, so we're going to have this formula, this expression which we have obtained already. If this molecule does not have a dipole moment, but it's only polarizable, then this molecule is going to interact with the ion by this part of the expression. You see that you have the charge of the ion here, the polarizability, and the inverse fourth power, and all the constants. So this formula immediately gives you how any molecule would interact with an ion. It can be dipolar molecule, it can be polarizable molecule. It's a freely rotating molecule. Any ion with any molecule is going to have this type of interaction. So you see that we're building on generality here by going through these expressions. In the previous lecture, we knew only how a dipolar molecule interacts with an ion, which is not a likely case. Now we know how any molecule interacts with an ion. Yes, Kiran?
If we have like a non-dipolar molecule and it's polarizable,
right?
And then do we have the U square part because of the induced polarization in there?
No, I mean, no. This
is just two separate parts.
No, when the molecule does not have a dipolar moment, this is all the interaction that you get, and the reason is because you see the tumbling, the rotation in this case does not really matter. So you can see that the KT is included only here.
Okay.
Now this interaction is not KT dependent. If you remember, KT came because the molecule, KT is the one, the thermal energy which makes the molecule tumble. However, if you have a polarizable molecule, this molecule is polarized at any orientation respective to the ion, right?
Okay, yeah.
Which is a bit of approximation because the molecule typically would have a non-isotropic polarizability and so on. But assuming that it's let's say that is not an important effect, whether the polarizable molecule is like that or like this does not matter. It's always going to be polarized in the same way. The dipole is going to be the same whether it's like that or like this for that matter. So that's why the polarizable part of the formula does not have KT. KT comes in the one that describes the orientation of the permanent dipole. And while we are at on that page, I mean, we can very much go and consider the general expression for interactions between two molecules which can be dipolar and polarizable. How does it work? So this molecule, this dipole has some field which in this orientation is more likely to be positive because the positive side of this molecule faces this one. Now, the way I have drawn it here, actually there is some, now do you see any error or not? Right, I mean, this is, of course, I've drawn the schematics, but the minus should be here, of course. This is going to be the negatively polarized end of the molecule. The one that faces the positive charge is going to be polarized negatively, so they attract each other. But this formula is not only for the case when this is a dipole and this is polarizable. This one can be a dipole, this one can be polarizable, or both can be dipoles and polarizable molecules. So the formula itself, again, you can see what we have here. A set of constants, r to the 6th power, which is the case between dipole-dipole interactions. Dipole-dipoles are weak interactions. They don't operate over long distance. And then here, this is essentially, this gives you the dipole moment of the first molecule times the polarizability of the second molecule. This is the polarization component which the first molecule exhibits on the second one. Plus the dipolar moment of the second molecule times the polarizability of the first molecule. So this is the force which comes because the second molecule polarizes the first one. So again, the first component here is the interaction because the first dipolar molecule polarizes the second polarizable molecule. And the second one is here is because the second molecule, which may have a dipolar moment, would polarize the first molecule and attract towards it. I'll give you time for questions, but before that, now again we know that the alpha, the polarizability, is expressed by electronic and molecular orientational polarizability. Now, how do we obtain from this formula a formula which we know before? Right. If the alpha of both molecules is 0 and they're the same, they have the same dipolar moment. When you put in this expression for alpha here and here, and have the indices 1 being equal to indices 2, then you're going to obtain this formula, which you obtained in the previous lecture, and which is the Chiasson energy of interaction between two dipoles. So now you know that the formula that we have obtained in the previous lecture is actually a simplified version of the full formula for interaction between any two molecules, which may be polarizable and dipolar. This is the general formula which describes any types of molecules with dipole moment and or polarizability. Any questions so far here, SRT?
Shouldn't that be like alpha 2 instead of alpha 0 2 there?
Yeah, alpha 1 and alpha 2.
I just used I just used the expression from Izrevashvili, which you choose this one. Actually, if you, I guess this one should be total too. Yeah, I have to check this actually. I'm a little bit insecure here. In principle, when you plug in this one, you should obtain the other formula. Obviously, if it's only 0, you're not going to obtain the other formula.
Yeah, no, because you lose that factor of 2 because you get a 2 on the top.
Right.
It works. So
it works.
Right.
But this should be really, the 0 should not be present here. The way it's written, it should be this. Just the notation doesn't match. This should be alpha total of the second molecule and alpha total of the first molecule. I don't know whether this is a mistake in Izrevashvili or just the way I have assembled the lecture. It appears this way, but that's how it works. Yeah.
In this total polarizability, if we have no thermal effect, so does this mean that it's basically an interaction between an ion and a dipole at a fixed angle?
Right.
So this should have an angle term in it, right?
No. Let me now. First of all, I mean you have thermal effects only when you have permanent dipole. Again, it's not that well seen here, but it's in the previous slide. This is the effect which comes from the thermal effect is when you have the permanent dipole. Now the other effect is when you have electronic polarizability. Now here I'm kind of like just seeing how this can match your question. Now the point is that any molecule is going to have polarizability. So this is always going to be present. Now you may have this component or not. So in a way, it's the other way. It works the other way to your question. You may have this component, which is the thermal component, or not. But this is always going to be present. Now, in a way, what you say here is also important in the sense that you can deduct the two by measuring possibly the thermal component of the polarizability. The non-thermal component is electronic polarizability, which is always present at any temperature. Now you can see that when you decrease the temperature, the polarizability is going to increase. And this is because you're going to allow the molecules to orient better and better towards their preferable direction.
That epsilon in there, isn't that also dependent on the polarizability?
The epsilon itself is
Or is it
it's a component of the polarizability. Actually, when we go a few slides further, I mean, they're going to be used interchangeably in a way. If you remember, I actually gave you the relation between the epsilon and the polarizability. This one here. So this is electronic polarizability. This is the basic polarizability of any molecule or atom. That's why epsilon, that's where epsilon 0 comes from. The other epsilon is related to the relative polarizability, it will be related to the properties of the substance. So it varies depending on the molecule, but you are all going to have epsilon 0, which is the basic electronic polarizability.
But the epsilon in there is dependent on the molecule, so it's a...
Yeah, it is dependent, but it's a molecular property which you, from the viewpoint of this class, it doesn't, I mean, you don't bother about this because this is something that comes from quantum mechanics and you don't care too much about it.
But could you express this thing in terms of just alpha 0 without the epsilon then?
Here? I guess you can. I guess you can, but then you're going to have more constants appearing, which is, so the expression is not going to look smaller. I mean, you can do that. Actually, you're going to see how we do that a little bit later. When it comes to van der Waals forces, that's used actually. Somebody else had a question on the back first. Okay.
Yeah, I have a question.
Uh-huh.
Like if there is no thermal part involved, that u square by 3k
Uh-huh.
is 0.
Right.
So the charge separation will always be in such a way that it's always like plus towards the, if the ion
Right,
is like
yeah.
positively charged, so there won't be any angle between in the dipole that will be formed, right?
No.
It will just be a charge separation to the same plane.
Yeah, it's in the first approximation that's going to be the case. In reality, if you have a non-isotropic molecule like that, I mean, it's going to be more polarizable in this direction than in this direction. However, from the viewpoint of this simple formula that we discussed here, the molecule has the same polarizability in any direction. And in any direction of the molecule, once you put, let's say, a positive charge here, the electrons are going to be attracted towards the positive charge. So the molecule is always going to have the kind of the negative side of the induced dipole is always going to face the positive charge. So whether it is this way or that way or whether it tumbles all the time, it doesn't matter because it's always going to be polarized in a favorable way.
So that's why there's no angle term in that alpha naught.
Right. Even if fundamentally it's even more important than this. This is the reason why the van der Waals interactions, at least between molecules, are always attractive. You have never seen of two molecules repelling each other at long distance. You have never heard about that, right? And the reason why molecules always attract each other is because when they polarize each other, they always polarize each other in a way which is energetically favorable. They polarize each other in a way by which they attract each other. So there is some very important fundamental kind of actually background here. We're going to see that this is not the case when they interact across media a little bit later though. Okay, just as long as we're not very far away from that slide. So right now we know we have studied these interactions the previous times and we have gone through these two interactions. And now we're in the place where we have only one single type of interaction, and this is between polarizable and polarizable molecules which don't have permanent dipolar moment. For example, you have two hydrogen atoms. Now a hydrogen atom doesn't have a dipole moment for sure. It's a spherical ball. Now the question is, could these atoms or molecules interact with each other? And is this interaction important? Daniel is having some doubts there.
Yeah, it depends on the temperature.
I think you're a little bit conservative here. The reality is that this is actually the basis of the van der Waals forces. So it's a strong and very important interaction. Of course, it will depend on the temperature, but it's going to be important. Now, the question is, how do they interact? And let's say we say, well, we've already derived this formula. If the dipolar moments of both molecules are 0, we're getting nothing. There is no energy of interaction. So how would they attract each other? And this, I mean, we have a few lovers of quantum mechanics here. So this brings us a little bit into quantum mechanics. Not too much. But then the system here is like two polarizable atoms. Now what happens here? Well, I mean, they're polarizable. What could they polarize each other? It's not immediately visible. However, let's say this one is a hydrogen atom. Let's see what do we have in a hydrogen atom. We have the nucleus, which is positively charged. We have the electron, which is negatively charged. And the electron, kind of in the simplest quantum model, just goes around the nucleus. On the average, you don't have a dipolar moment. But if you just freeze the system, like for a fraction of a very, very small fraction of the second, the electron is here, the nucleus is here, so we have a dipole. This dipole kind of rotates and moves around all the time. So on the average, you don't see a dipole, but temporarily we see a dipole. And this dipole can eventually polarize the other molecule and vice versa. Kind of, can you imagine this?
It's like a series of instantaneous consecutive dipoles.
Yeah, what actually, to be more precise, what happens is let's say you have two molecules and then the electrons vibrate and rotate around the molecules. In a way, they begin to couple their rotation and vibration. So they also have this favorable dipole-dipole interaction. So when, let's say, one of the nucleus is like that and the electron is here, then the other nucleus would be here and the electron would be here, so they have a little bit of dipolar attraction. Then they're going to rotate around, but they're going to try to still kind of polarize each other and interact favorably. And this has been one of actually the biggest insights in colloidal science, not colloidal science, molecular science, done in the of course more than a century ago. Now, what I have shown here is some simple estimates. Now, we have instantaneous dipole. Now, the dipolar moment is equal to the charge times the distance. We can say that we can have this so-called first Bohr radius. It's a model, but you can say this is the average distance between the electron and the nucleus in a hydrogen atom, for example. A0. The charge in this case is one electron charge, because we have one electron circling around, right? And if you calculate this, that you're obtaining that for hydrogen, you are going to have an instantaneous dipolar moment of 2.4 dBs. And if you remember, just from the numerical values which I told you in the previous lecture, that's a lot. So it can be instantaneous attraction, it can be very fast and temporary, but it's a relatively strong attraction. And again, for the quantum chemistry lovers, mechanics lovers, now the energy of a positive and negative charge separated at a distance A0 is this one. This is Coulomb energy. It actually can be derived from the formulas about Coulomb energy that we derived the previous time. This is positive and negative charge attracting each other. This energy, however, from quantum mechanics can have only specific values. And these specific values are essentially quantized by this h times n, where n is the vibration frequency. So we say, okay, we know that now the vibration frequency is something that can be measured by spectroscopy. So when we express this and take the values for hydrogen, we obtain that the distance, this first radius, the radius of the first electron in a hydrogen atom is going to be 0.053 nanometers, which is not much, but this is the source of the dipole that we get. So we know what is the distance, we know what is the charge, we have an estimate of the energy. So from what we can do from here on, actually we're not going to do this explicitly because it's more complex than that, but we're going to see right now where this leads us to. And this leads us to very similarly, we can put in the values in the formula that we already have. We can put in the values for the instantaneous dipoles. Now what essentially in order to obtain this formula, you have to use those two formulas. The dipole moment of a hydrogen atom is equal to the distance times the electron charge. We derived this quantum mechanical formula in the previous slide. We also know that this is the relation between the electronic the electronic polarizability and the electric constant of the material. Again, the radius here is the radius of the electron. So after calculations, tedious, you have to remove the electronic charge out of that formula. You do these calculations and you are going to obtain this formula to the precision of a constant. So you're not going to obtain exactly the same constants that you have here, but you're going to obtain exactly the same formula. And the reason that the constants here is difficult because historically this is the famous London's equation for the dispersion forces between two similar atoms or molecules. This has been derived again like about a century ago. What I have shown here is the formula for the similar atoms and dissimilar atoms. Again, you see here that you have a single quantum, something that comes from quantum chemistry, the vibration frequency of the electron around the nucleus. Now, we're going to go to this a little bit later, but this is also true for molecules. Because for molecules, there's always going to be this outer electron, which is furthest away from the electronic center of the molecule, and it's going to be most important for the dipole moment. And these are the equations, this is the last set of equations that eventually we needed, which describe the interaction between two polarizable molecules only if they don't have any dipole moment at all. And now is the time to ask questions about this part of the dispersion forces. Let me prevent some of the questions right now by telling that this is obviously this was done just in a very simple way, kind of rule of thumb quantum calculations in order to feel the physics. Obviously, you can go to much bigger depths than that, and I'm going to go to that topic a little bit later when we discuss the Hamaker constant. But so far we know how we have a formula how they interact, and again notice that the dependence on the distance is the inverse 6 power. And from our viewpoint, what we have here are good constants. These are molecular constants which can be found in different textbooks, handbooks, and so on. So if we need to calculate that energy, estimate it, we can do that. I mean, it's not difficult. Okay, any questions? Okay, so we're fine. We have gone through all different types of energies of interaction now. We can do any type of imaginable interaction between two molecules, ions, dipoles, whatever. Now let's see how this relates to all practical applications. Now before we do that, let's go through this checklist again. Kind of make sure that we didn't miss anything and remind you all where we have been. Now, the covalent metallic interactions are something that are not common in colloid science. They are very complex, so we decided that we're going to discharge them. I mean, you didn't decide, frankly, but I mean, I decided that I'm going to discharge them. So we're really that this is not relevant to this course. We know about charge-charge interactions, charge-dipole interactions, dipole-dipole interactions, non-polar, dipole non-polar, and the last one, two non-polar molecules, is the van der Waals forces, dispersion energy here. We have only one item here on this list, which we have not studied this far. And this is the so-called hydrogen bonding. Now, some of you should have been to the seminar on Monday. And if you have been to the seminar on Monday, this is the chemical engineering seminar, you have seen how people do very complex calculations in order to understand how water molecules eventually form different structures. Now, structure is something that we don't like very much in simple colloidal science because it calls for very complex calculations. So for now, until we're going to come to this point again where we, a little bit later when we discuss hydrophobic forces and interactions. So this type of interaction can be very important between water molecules. For now, however, we're just going to observe what happens because we have hydrogen bonding in some cases. And certainly we're not going to go into the quantum details about hydrogen bonding. What you should know is that this is a strong structural force. And actually you're going to calculate a little bit of interactions about that in the homework, right? I don't see many enthusiastic response about the homework, but this is because you haven't done it yet perhaps. But one of the problems is just estimating the energy of interactions of dipoles. Yes, Brian?
It's sort of the same point that RT made last time. Is this a alpha? I'm sorry. If you go back to the previous page, is that an alpha 2 and an alpha 1 in the numerator of the equation on the left?
I think that this is actually the form where it should be alpha 0,1 and 0,2. That is the molecular polarizability, the electronic polarizability rather than the full polarizability. It's a good point. Let's check this for the next time. I think that's where it should be 0, and in this general formula it may not be 0 because you also have orientational polarizability. And actually we're going to go to these formulas right now, back, because what I have done here is to summarize the three most common types of interactions together. Now again, in colloidal science you don't deal with ions too much, at least not in the viewpoint of interaction between particles. Usually you don't study interaction between, let's say, sodium chloride crystals. Usually you study interactions between dielectric materials. So in dielectric materials you don't have charges in typical unless they are on the surface. You don't have an ion embedded in polymer, inside the polymer. You may have a charge on the surface, but you cannot have a material which has embedded ions inside. So from the viewpoint of colloidal science, the interactions that matter are interactions between dipolar and polarizable molecules. And what I have done here is I have taken out this term, where we have all common constants. I have summarized all three terms as a sum in here. And then we have the common r to the inverse r to the 6th power here. And this makes us happy, because if we examine these terms, now you may have them or you may not, but if you examine these terms, these are simple molecular parameters, which are fixed and constant. So when you study interactions between molecules or between particles and so on, you can say, well, I either know this or I don't care about this because these are constant. They may change a bit with temperature because of this dependence. But as long as I work at constant temperature, I can say all those are three constant. I can take these three constants as something that I may know or may not, or I can bundle them into a single constant. And then all the molecular interactions which I care are dependent on this simple constant and the sixth power of the distance between the molecules. And this is very good because you don't want to do very complex multiple calculations and so on. you want to be able to do a very simple potential. And this potential is equivalent to what? Right. I mean, we have by molecular and quite extensive molecular estimations, we have essentially derived a formula which, when simplified, leads us back to the Lennard-Jones potential. You can say, well, I mean, we've known about the Lennard-Jones potential before. Why did we have to go through all this? But the reason we had to go through all this is to understand the physics. And thus we're going to see this physics here emerges over and over in different cases later on. So in terms of understanding, it's important. In terms of exactly how do you use these formulas, this is not that important. And in many cases, you're not going to even use this to calculate. In many cases, you're going to use just simple constants from the literature, and I'm going to show this constant. It's called a Hamaker constant. But so far, we have derived the formulas that we want. Let's move on and just consider some cases. Now, you have to watch at your notes, obviously, here. We have derived these three different types of interactions.
I was wondering what the derivation for the repulsive part of Lennard-Jones potential.
We're not going to deal with that. And the reason we're not going to deal with that is because we want to understand the interaction between colloid particles, which are typically attractive. The repulsive part from the viewpoint of colloid science is so short range that it doesn't matter. Two colloidal particles in suspension attract each other by van der Waals attraction or repel each other by electrostatic charges on the surface. But the repulsive interactions don't matter because once they touch each other, they're not going to separate, as we're going to see, because they are aggregated and they're going to stick together, and that's it. So from the viewpoint of colloidal, these complex short-range interactions don't matter. And also from the viewpoint of many of the other cases in which you need to know molecular interactions. For example, this is one very instructive formula. What are the components of the dipole-dipole, orientational dipole polarizable, and purely polarizable component for different couples of molecules? Neon. You know that this is a fairly symmetric molecule. You wouldn't expect it to have a dipole moment. Dipolar moment 0. All of the interactions are purely polarizable interactions, 100% dispersion energy contribution. You go then to more complex molecules which have dipolar moment. You can see that the dipole-dipole and dipole polarizable interactions increase significantly. But what you're going to find out is that the dispersion interactions, the polarizable components, are as a rule always higher than the dipolar interactions. So even though the dispersion interactions may look as kind of the weakest, just temporary dipolar attraction because of the electrons that move around, actually they're the strongest interaction in molecular physics. And then you go here to the last row of the table. Let's say this row, let me delete that so we can. Now look at this third row. We have, this is tetra, okay, this is chloromethane. It has a very high dipole moment. When we do the calculations, we find out that 70% of the interactions are dispersion forces. So 30% are dipole-dipole interaction, and you can see that the dipole-dipole interaction in this case is strong. Then you go to water, which is the last one here, and you see that the dipole moment is not very large. And yet when you go to the dispersion energy contribution to the water molecule interactions, you suddenly find out that the dispersion energy contributes only 24% to the interaction between water molecules. So water molecules are in a way unique. You know that the water is the unique element, the unique molecule of life, but you can see that it's also unique from the molecular viewpoint. Now, what is the reason for the wall dispersion contribution of water-water interactions? Right. I mean, this is hydrogen bonds. Water interacts by hydrogen bonding rather than by dispersion forces. And so far we have been discussing molecules which interact through vacuum. Now what happens, and this is very important because this is going to lead us to different types of dielectrophoretic research and so on. What happens when we have a molecules which interact through medium? The polarizability in this case is going to be dependent of, you know, this part of the 4 times pi electronic polarizability, size of the molecule on the 3rd power. But then you have this new component here, which gives us the difference between the dielectric permittivity of the particle or molecule and the dielectric permittivity of the medium. And then when we substitute this formula for the polarizability, for example, in the potential of interaction between an ion and a polarizable molecule, again this term appears here, and it leads to what? It leads to the fact that the molecule, the interactions can be repulsive or attractive. Suddenly, the interactions which were only attractive can become attractive or repulsive because of the effect of the medium. If the medium is less polarizable than this molecule, then these two molecules would love to attract each other, or ions or dipoles. However, if the medium is more polarizable than the molecule, the sign here in front of the energy is going to inverse itself. So we're going to have a repulsive energy between the molecules or the particles. In a way, the kind of a very rude expression about this is the molecules love the environment more than they love each other. They love to interact with the environment and they don't love to interact with each other. And vice versa. Now there are some, let's say, some relevance to male-female relations here, very broad, which relates to the environment, relates to how much you may like some specific person. If all the persons around are worse than him, or her, you're going to like him or her. If all the persons around are great, you're going to dislike this specific person just because of the environment, right? In a very similar way, it comes to molecules and polarizability. So you have to have this keep this in mind from when you do interactions in a third medium, which is always the case with colloids. You have particles interacting through water or oil or whatever. Questions? Okay, we're very close to finally getting something practical here. This didn't look like that on my slide. And what you had here, you had these small volumes, very similar to the image that we had before. So this is the distance between these two volumes. Now, dispersion forces need not be additive and need not be pairwise. If you have 3 molecules, these 3 molecules are going to coordinate their electronic polarizabilities in a way to account for the 3 of them. Obviously, this makes calculations very simple, so that's why Hammaker has proposed that essentially all types of van der Waals interactions are handled by pairwise additivity. So what we're going to do next time, in the next lecture, we're going to discuss for different objects of specific symmetry how we can do the integration by substituting this potential here on the van der Waals potential, and then integrating over all of the volume of the interacting particles or media or slabs or whatever. So all next time we're going to actually study this integral. Right now, however, we can immediately see that there are some points that have relevance here. Now we can substitute the van der Waals potential that we obtained in here in that formula. We can assume that the particles are homogeneous of density, so the density is not dependent on the coordinates. And then because this is a constant, these constants come in front, multiplied by the densities of the two particles or interacting media. And finally, historically, what Hamaker has done, he has added pi squared here, just because pi squared is going to appear very much here when you use radial coordinates. When you do the integration, you're likely to use radial coordinates. When you put radial coordinates, the pi always appears from the one coordinate, another pi from the other coordinate. So pi squared is likely to appear here just because of the coordinates. So we can take this pi squared times the van der Waals constant times the densities of these two interacting particles. And this is what you have, what is called Hamaker constant. I guess you have heard this term already, in one aspect or another. Hamaker constant is actually the constant which you need in order to characterize the interaction between two particles or different types of films, materials, and so on. So molecular physics people would use van der Waals constant. Colloidal people would use Hamaker constant. So all you need to do is know this Hamaker constant. So in the end, in the remaining time of this lecture, we're going to discuss how we calculate Hamaker constant, how we use it, how we estimate it, and so on. And again, you have to watch probably at your right up here. We discussed that different materials mediate the interaction in different ways. So the interactions through different media would not be the same. This is a very useful summary of all types of interactions between, so let's say you have air, water, air. So you have a thin slab of water between two air phases. What is the Hamaker constant of interaction here? Now all of those constants are multiplied by 10 to the minus 20th joule. So this is just the permanent, the variable part. Now the first thing that you can see here is that the Hamaker constant typically, when we have symmetrical system, is in the range of 0.5 to 4 times to the minus 10 to the minus 19 joules. In order to understand how important this is, you can compare it to what? To kT. kT is 2 orders of magnitude smaller. So van der Waals of the interactions are always going to be strong interactions. Unless the objects are far apart. When they are far apart, because they decay fast, they're not going to be important. But if the objects are closer, they're going to be important. So the closer they are, the more important the van der Waals interaction. Now let's just take a look at some of the numbers here. Now air is essentially nothing. So water compared to air has a very high interaction. I mean, essentially water would like to attract each other. Water droplets through air or air bubbles through water would like to really separate each other. So the van der Waals constant is going to be strong. Now we'll go to liquids. Two liquids like pentane, water, and pentane are really not going to love to be separated. Pentane would like to get away from water, as you know. But this is nearly not as strong. Let's say the interaction between two pentane droplets in water is going to be about an order of magnitude weaker than the interaction between two air bubbles in water. Same for other liquids. We go down here. Okay, I mean it's always small, and suddenly you get something which is larger. Alumina, water alumina. Alumina is already a solid body. Solid materials, especially one which has some oxide and so on, are going to be polarizable. So suddenly we come across alumina, which tends to be very interacting just because a luminance has high polarizability and would like to stick together. And then we go further down, and suddenly we reach the place of, suddenly there is another shock here. A van der Waals constant which is 10 times stronger than anything that we have seen so far. And this is of interaction between what? Actually, sorry, we come, okay, no, the right one is here. This is root L. Suddenly we come to a van der Waals constant. There is no theoretical basis for that. We come to a van der Waals constant which is 30 to 40. And this constant is between what? Interaction between what? Where is Kedon? Where is this constant?
Gold nanoparticles.
Right. So suddenly you can see that metals have enormous van der Waals constant compared to everything else. It's an order of magnitude larger than anything that you can see with the exception of some solid bodies. The reason for this is the metals have very high polarizability. So now let's say we have given some answer to why metal particles would stick to each other in water. Their interaction is order of magnitude larger than other particles. And then we move on here where we have asymmetrical systems. We have one type of phase interacting with another type of phase through a third type of phase. And suddenly we can see that we can have a variety of negative constants. And negative constant, when we put it in the formula, would mean repulsion. It would mean that if we have, for example, note here, solid surface, liquid helium fume, and vapor, the interaction between the vapor and the solid surface kind of is going to be repulsive. So the fume would like to get thicker. Again, if we have, let's say, pentane, water, pentane, if we have two oil droplets in water, they would like to stick together and separate from water. However, if we have liquid helium, solid surface, and vapor, we are going to have quite strong repulsion actually, which in this case corresponds to the film would like to get thicker. So how is the film going to get thicker? By sucking liquid helium from the vessel and wrapping itself around the vessel. And as you may kind of immediately guess, this is the reason why liquid helium falls out of vessels. The van der Waals constant of liquid helium on any surface, with the exception of a very few elements, and they are very exotic ones, is negative. So liquid helium, the only ones are I think sodium and some alkane elements. So liquid helium would not fall out of, let's say, sodium, vessel made of pure sodium. Any other vessel would be essentially would make the liquid helium make a fume and fall around. And there is not much that you can do about this, even if you know about wetting and so on, because the basics really comes from the molecular interactions and the Hamaker constant. Okay, any questions about this part of the? Okay. Just a little bit further on, to move on again these types of interactions. I won't derive this, which is can be immensely tedious derivations. In the case where you don't know the interaction, the van der Waals, the Hamaker constants for different types of media, different types of phases. People have been good enough to derive a number of approximate expressions, which are very important. Not so much even in terms of deriving the constants, but as much as giving us insight on the physical behavior of many systems. So when you have phase 1 and phase 2 interacting together, you can think of this as just a thin layer of vacuum. The Hamaker constant of interaction of phase 1 and phase 2 is going to be approximately equal to the geometrical mean average of the two Hamaker constant for the pure phases. So in the unlikely case where we have to calculate the Hamaker constant for the interaction of something very unique, which you don't know, the Hamaker constant, you can take the Hamaker constants for the pure substances and get the Hamaker constant for the interaction by taking the geometrical average. Now, we discussed that the Hamaker constant for a pure substance through vacuum can only be what in sign? Positive. Anything in vacuum attracts to itself. So because we derived the interaction between two phases by the interaction through the pure phase in vacuum, and this can be only positive, this means that two phases can always have only positive, only attractive interaction. They are always going to attract each other no matter what the phase is. So anything pure attracts to itself, and any two phases would attract to itself in vacuum. Now then we go to the symmetrical phase, to the symmetrical case, phase 1, a medium of phase 2, and then phase 1 again. The approximate expression here tells us that the interaction in this case can be derived by the square of the difference of the square difference of the square roots of the constants for the phases 1 and 2. And again we have a number of very important conclusions. We have squared here. So no matter what this constant is always going to be attractive. So two similar phases interacting across a third phase are always going to attract each other. No matter what the third phase, and no matter what the phases which interact. So it's not only in vacuum, but anything attracts to itself in any other environment than vacuum. From colloidal viewpoint, any particles would like to, if they are of the same material, would like to get together. In any environment, in any media. You can't adjust the media to make the interactions between the particle repulsive by van der Waals interactions. And van der Waals interactions are always present, so anytime you have particles, there is no chance of making them attractive. The only chance that you have is to adjust the constant of the media to be the same as the particles, in which case they are not going to attract each other. Now, this expression is also symmetrical. You don't care whether this is A1 or A2. So this tells you that if you exchange the phases, you're going to have the same interaction. So water bubbles, so air bubbles interacting across water would interact exactly in the same way as water droplets across air. This is also very important. And because you see that here actually the second Hamaker constant always decreases the effect of the first one, the strongest interactions would be in vacuum. The higher the Hamaker constant of the media itself, the lower the interactions between the particles. Yes, Chris?
What if the dielectric of 2 is higher than dielectric of 1? Like you were saying how...
If it's higher, then you are going to have, like, I mean, this is going to be positive, this is going to be negative, but we have squared here.
So the 2's will attract each other.
So it's always going to be attractive. It's always going to be positive Hamaker constant. Now, how this works, again, let me remind you that the interactions would be proportional to the Hamaker constant over the radius to the 6th power. And you have minus here by default. If the Hamaker constant is positive, the interactions are going to be negative, which means attractive. If the Hamaker constant is negative, then the interactions are going to be repulsive. As long as you have positive Hamaker constant, you're always going to have attractive interactions. And you see that in all those cases where we have only two phases, or where we have symmetrical phases, the Hamaker constant can only be positive. And if you invert the system, you're still getting the same Hamaker constant by value.
The one that isn't that one formula you had where the
This one?
A would have been proportional, the Hamaker constant would have been proportional to the epsilon of I minus epsilon of the solvent.
Right.
So in that case, it would be,
3 slides before this.
is that not the same?
I'm going to show a little bit the dependence between the Hamaker constant and the epsilon in the next slide. But the point is that for any pure material, you have a certain Hamaker constant. It's always positive.
Okay.
These two can be smaller or larger, but because it's squared, it's always going to be positive. And you can estimate them polarizability. And finally, if you have unsymmetrical film, this is already more complex expression. You can have any type of interaction, either positive or negative. And now, regarding your question about the relation between Hamaker constant and polarizability, now there is the enormously complex theory started by McLuhan and then finished by Lifshitz, which actually deals with the real quantum details about the interaction. You don't have only one electron in a molecule, you have many electrons. If you want to understand the Hamaker, the van der Waals interactions, you have to sum up all the frequencies of all those electron orbitals, quantum states. So the real van der Waals interaction is a sum of the quantum state of all electrons in the molecule. You can simplify that. You can replace the summation of by quantum levels by integration. You can put in this here, which tells you what is the interaction between the third media. And finally, because very often you don't measure polarizabilities at high frequency. Now, if you calculate what are the frequencies here, you're going to find that this frequency are in the visible region. And instead of trying to measure the polarizability by electrical means in the visible region, what you do in the visible region is you measure refractive index. So then the polarizability are going to be dependent on the refractive index. And I really don't want you to try to understand all that derivation. If you want, you can read the 3 corresponding chapters of Izraelashvili. But I want you to try to get the basics here of that formula, which relates the Hamaker constant of a symmetrical system to the polarizability of the two media and the refractive indices of the two media, of the two phases that interact. Now, as you can see, the Hamaker constant would have two components. One is dependent on electrical polarizabilities at zero frequency. One is dependent on the refractive indices. And now again the award for fastest and most physical thinking here comes to somebody who can relate those components to the different components of the van der Waals forces which we studied just through this lecture. Which corresponds to what? Okay, we studied dipole, okay, dipole-induced dipole, and polarization just without dipoles. Which you would think corresponds to what here? Okay, let me tell you the result. We don't have that much time. Physically, when you have dipoles, you always have polarizability at any frequency. Even if you apply constant field, the dipole would orient itself and polarize. When you have van der Waals forces, you have the electrons moving at high frequencies. So the purely dispersive London interactions are the ones which are expressed by the refractive index. All other types of ionic and dipolar interactions are the ones which are expressed by the polarizability. So for example, and then you have this complex frequency chart where you have the polarizability, the permittivity as a function of frequency. If you take hydrocarbon, this hydrocarbon is going to have very smooth polarizability. If you take water, the water is going to have high polarizability at low frequency. And then in the visible region, it's going to have slightly more polarizability than hydrocarbon. What is the reason for the water having this very high polarizability compared to hydrocarbon at low frequency? The reason is that water has a permanent dipole moment. Now, let me finish here just with one last and important note. If you want to compare the Hamaker constants of two phases, you don't need to measure the Hamaker constants. You can take the polarizability and the refractive indices. If the phases have the same refractive indices, they're going to have the same Hamaker constants, unless they have high polarizability, which is not likely for most of the common substances. So two polymers, for example, are going to have exactly the same Hamaker constant, exactly when they have the same refractive index. And this is one very simple rule of thumb way to compare Hamaker constants and obtain them. You can take a look and kind of go yourself through the summary of the lecture later. Let's finish off for now. I think I've piled enough on you for this lecture. Thank you for your attention. Okay, any questions? I mean, like, we have to formally finish, but if you have any questions, I can still answer them. Or you can drop by and ask them here. Now, this was the most, I guess, theoretically complex part of the course. I mean, from the next time we're going to really go on application, how we do use and apply those things in real systems. So.